Hello, everyone. This is a very cool session that I was voluntold for. My name is Fadil Adib. I'm a professor at MIT, currently on sabbatical doing a startup. And we have a fun session today on BGP configuration with 4 papers covering different aspects of it. Like in the previous session, each talk is 10 minutes, followed by 2 minutes of Q&A, where we can take quick questions. And if we have time at the end, we'll also have a mini panel where the presenters can ask each other questions, and we can also take a few more questions from the crowd. The first talk is by Tibor Schneider, who is a third-year PhD student at ETH Zurich, advised by Laurent van Bever. His research aims to improve network operations using formal methods. He'll be presenting on taming the transient while reconfiguring BGP. Timur.
Thank you. So let's put yourselves in the shoes of a network operator. You're operating that network here. It's very small. It has two neighboring peering networks. Both peering networks advertise prefixes via BGP, but the network prefers routes towards the left due to a higher preference. Now let's say you have to remove the BGP session on the left due to regular maintenance, but you want to do so without affecting customer traffic. So you could just simply remove the session, but what that would do is it would create a black hole at the left border router because the router doesn't yet know about the alternative route. But eventually, as soon as BGP converges, it will know about the route, and all the routers will forward to the right. So it is only a transient issue. But still, we performed measurements and saw that the reachability is only restored after 2 seconds, and that in a very small network with only around 1,000 prefixes. So we can perform this reconfiguration a bit smarter by first moving all the traffic over to the right before performing the reconfiguration. And we can do so by lowering the preference. And this is actually what best practice suggests in this case. So this is actually a big improvement, as we can now no longer have any black holes, but still we can transiently get forwarding loops. And this is because BGP converges in a very chaotic way, and BGP directly drives the forwarding. So maybe we can decouple the control plane from the data plane during convergence, so that we can perform the reconfiguration safely. And a technique that does so is called chips in the night. And what it does is it introduces the final configuration along with the initial configuration. But while the initial configuration still drives the data plane, so the final configuration is deactivated. Then it will wait until the final configuration has converged, and finally it will activate the final configuration, but one router at a time in an ordering that preserves reachability. So this indeed works, and this technique can preserve reachability for any kind of reconfiguration, but essentially it duplicates the entire control plane, so it has a large overhead. But maybe we can achieve the same decoupling of the data plane and control plane without duplicating the control plane. And we could do so by using static routes. So the idea is that we push static routes everywhere in the network, which would then fix the initial forwarding state. And then we can just reconfigure BGP and let it converge without it affecting the forwarding state. And then finally, so we let it converge, and then finally we just remove the static routes from right to left until the network is reconfigured. While this does work, the problem is that during that time, the network is vulnerable to unforeseen events because those static routes cannot react to failures and they would just drop packets. So what we want is we want to reconfigure BGP, but we want to do so efficiently without requiring lots of resources, but we also want to keep the reactivity that is inherent to BGP. We want to do so safely, meaning that the specification that we give it should be satisfied during the entire reconfiguration, also in any transient state. And we want to do so in networks today, without extending the protocol BGP itself, but by relying on its basic functionality. So what we propose in our paper is a technique that solves this problem. And we achieve efficiency and reactivity by keeping the data plane and control plane coupled to each other, compared to related work that decouples them. Instead, what we do is we control how BGP converges, and we do so only by changing route preferences in the network. So we want to control how BGP converges, and we do so by controlling each router individually when it updates from the initial route to the final route. So for one single router to update in a controlled way, we identify three sufficient properties. First, the router must select the initial route. Second, it must receive the final route without yet selecting it. And third, and most importantly, updating the router cannot cause any other router in the network to update. So let's look at the example from before to see how those three rules apply. But now I'm not showing the forwarding state, but I'm showing how BGP propagates in the network. So here we have the initial route here in blue that is advertised to the left border router and propagated from there inside of the network. And we also have the final route in orange that is advertised to the right border router. So this right border router here, shown in green, it selects the initial route in blue. It knows about the final route in orange. And also, for every other router in the network, they would always prefer the blue route over the orange because it has higher preference. So what we can do is we can make that green router update. And we do that by just changing the preference of the blue route. And so we can lower it, but just add the green router, and then that would make it update. And now we are at a state where every other router still selects the blue route, but also knows about the orange one. And we can repeat the same procedure for the others. So that works, but it only works it is not always that easy. So BGP has many features that allow it to scale to very large networks, for instance, route reflection. And these features essentially reduce route visibility, which means that some routers don't know about the routes that others select. So let's look at the same example here, but now we have a single route reflector, here shown in red. So this reflector now receives the initial route in blue from the border router and then reflects it inside of the network. We can do the same thing as before with the right border router, making it update, but then we are stuck because the route reflector now is the only one that selects the blue route, knows about the orange route. But as soon as we make that one update, it would also cause the other routers in the network to update because it would replace the blue route by the orange route. So what we do to solve this issue is we temporarily adapt the propagation graph and to increase the route visibility wherever needed. And we do so by adding temporary BGP sessions. So for instance, here, the router at the bottom, we add a temporary BGP session so that it will receive the final route, so we can make that one switch. So what we do is, in our paper, is we present Chameleon, a system that generalizes the idea from before and automatically reconfigures BGP networks. It takes as an input the configuration and an arbitrary reconfiguration scenario. And this scenario can be as simple as adding or removing sessions, or it can be changing certain route maps in the network, or do multiple of those things together. It also takes as an input the specification, which can be just reachability, or it can contain properties like isolation or waypointing, and a combination of those with Boolean or temporal logic. And then what Chameleon does is it computes a schedule of nodes and when those should update. And this schedule should follow the three rules that I've talked about before so that we can control how BGP converges. But it also must satisfy the specification at every time in the reconfiguration. Further, we want that we can perform the reconfiguration quickly, so we want to do multiple things. We want to update multiple routers concurrently, and we want to minimize the number of temporary BGP sessions that we add. So what Chameleon does is it formulates a optimization problem and encodes it in an ILP to solve it efficiently. And the solution to that problem is a node schedule that says when each router should update. Chameleon, in the next step, applies this reconfiguration to the live network by enforcing that schedule. And it does so by generating commands that are simple BGP reconfiguration commands that just change route preferences. and it applies them to the network. And it also generates conditions that check if BGP has converged sufficiently. And as soon as it has converged sufficiently, it applies the next set of commands, and it repeats that until the network is fully reconfigured. So in the paper, we present a large-scale evaluation, and as a quick summary, Chameleon is able to schedule a large-scale reconfiguration that contains, that affects around 100 routers in less than 5 minutes, and it's also able to perform that update in less than 5 minutes. So finally, you can try Chameleon out right now directly in your browser. By following this link, you will see a simulator that shows the forwarding and routing states of the network during convergence, and so during in transient state. And it will show the commands and conditions that Chameleon will generate, and it will allow you to perform the reconfiguration as Chameleon would. So now I'm happy to take any questions.
To things like network failures that occur in the midst of the reconfiguration. But what actually does happen when failures occur using your tool?
So the failures are the normal failures that would happen in a network, if I understand. So you're asking whether...
You're in the middle of orchestrating, you know, a series of configuration changes, and then something fails while you're doing that. So is your tool actually robust to that?
So,
and what is the end state when that happens?
So it's a very good question. So indeed, it's challenging to even characterize or like say how robust the system is against certain events. For instance, when the initial configuration isn't really robust against some events, then how can we be robust in between? So there certainly exists events, like, maybe the addition of a new route or the withdrawal of an existing route that could introduce temporary issues. But most or many of them, the system can handle, like link failures or so. And we propose in the paper, we propose a runtime controller that also monitors the network to react to those failures if it sees that they could cause any issues. But we can take the question offline.
Yeah, it's going to be pretty detailed.
Thank you.
So.
Hi, Psychiatry from Meta. I was wondering that the two questions came in when you had the motivating example. One is that you do not have a fully meshed BGP because you want to limit the number of sessions. That's the whole point. If you do want an additional session, you might as well have a fully meshed BGP instead of RR. And even with route reflector, you have add path. And that would basically solve whatever you're trying to do. So I understand you're not exactly, your solution is just session bring up and so on, but I didn't quite understand how they will work or why do we need it in real life.
So you mean that why I need temporary BGP sessions? Or?
Yes, so you said that the RR is only sending the best path to the rest of them, but if you use add path extension, which has been more than 10 years now, I think, it will send all paths, so you would not need anything else. And even in other cases, if the routers do want to support transient session, it might as well do a full mesh BGP. Then you do not have this problem to begin with.
Yes, I agree with you. And in that case, Chameleon wouldn't need to add those temporary sessions, but it would just do without. Thanks for the question.
We should probably move on, and we'll have time at the end for more questions. So the next talk is by Alan Tang. Alan recently completed his PhD in computer science at UCLA, where his research focused on network verification. He's going to be presenting his paper, Lightyear, using modularity to scale BGP control plane verification. Alan.
So hi, my name is Tang, and I'll be presenting our work. So BGP is used to advertise routes between networks globally, and it's often configured with complex policies for business or security reasons. And as a result of this, when there's a misconfiguration, it can have major impact on internet traffic worldwide. And this happens quite regularly. Issues with BGP have caused numerous incidents in the past. So one way to remedy this problem is to verify with formal methods, and there have been various previous tools that attempt to do this. So they usually do something similar to the following. First, they take configuration files defining what each router should do. They take a user query describing some property to check, and then they build a model of the network using these, and different tools will build the models with different approaches. And then they'll check the property, and either the property is verified and everything is good, or the tool finds a case where the property doesn't hold and returns a counterexample. However, a major problem with existing tools is that when they build the model, they model the entire network at once, and this leads to two problems: scalability and the ability to localize errors. So the first problem is scalability. So when modeling the whole BGP network, you have to consider the various possible combinations of prefixes and attributes at all the various locations in the network, and that can be very difficult when dealing with networks that are very large, potentially with hundreds of routers. The second problem is error localization. So existing tools can find a counterexample, but often we don't just want a counterexample. What we really want to do is we want to narrow down the cause of the error. So what router is the problem in, and what part of the configuration should we look at to investigate further? So we are proposing that the solution to these problems is to perform checks modularly. So previous tools model the whole network at once, so they cannot scale the large networks, and they have a hard time localizing errors. In our work, we instead model and check policies in the routers independently. And since, practically speaking, there's a limit to how complicated policies on each individual router is, checking them will scale roughly linearly in the number of BGP sessions. And since there's a separate check for every policy, if one of the checks fail, we immediately know which policy it is in. Of course, there is a trade-off, which is that when checking the whole network at once, we only need to know the end-to-end behavior. Whereas when doing modular checks, we also need to know what each local policy is supposed to do, which requires more information from the user. Our claim, however, is that this is usually still not very hard because there's usually a simple underlying structure that ensures a policy in the network, and this structure is usually independent of the size. And it's very difficult to maintain and understand networks without having some of this structure in the configuration. And as part of this structure, there's typically a small number of roles, so many local checks can be reused for different nodes. Previous tools don't leverage this structure, and the key idea behind our work is that when we have this information, checking BGP properties becomes very easy. So here's an example to show what I mean. Let's suppose we have a network that's connected to ISPs, and we want to show a node transit property, specifically that any route received from one ISP should not be announced to a different ISP. Using existing verifiers, we'd have to consider the various possible routes and paths that could be sent through the network, and that can be quite difficult. But in practice, there's usually an underlying structure to the configuration or some sort of mechanism to implement the property. So for example, what the network could do is that they could tag all routes that come from ISP1 with a particular community. And then once we have this information, we know what each router in the network is supposed to do for this. So we know that, for example, the R1, which receives routes from ISP1, should establish this structure by tagging routes with the community. We know that other nodes in the network should somehow maintain this structure by not removing this community from any routes. And we know that R2 should use this to filter out routes to ensure the property. So instead of reasoning about all possible network states, it suffices to check these simple local behaviors. So in our work, we present a general assumed guarantee framework for modular BGP verification, which allows checking end-to-end properties using only local checks on policies in individual routers. And we show techniques for verifying two broad classes of property. The first is safety properties, which hold when all routes reach a particular location, which holds when all routes that reach a particular location meet some criteria, and liveness properties, which hold when we can guarantee that a good route will eventually reach some location. We've formalized and proven the correctness of our approach, And we've applied these ideas and used them to check properties on a major cloud provider where we found numerous bugs in the BGP configuration, and to our knowledge, no prior tool works at a comparable scale. So here is a diagram showing how our tool works. Like previous tools, we take as input the network configurations and a property to be verified. But unlike previous tools, we also require network invariants or other constraints that encode the structure behind the configuration. And instead of modeling the entire network, we instead create a set of local checks that can be run on individual routers. If all checks pass, that means the property is verified, and if some checks fail, it will produce a counterexample for individual policies, making it easier to see what went wrong. To briefly illustrate how this works, let's consider the node transit example again. So the user wants to verify an end-to-end property that that routes from ISP1 are not sent to ISP2. In order to do this, we ask them to provide a network invariant which encodes the structure that we expect in the network. So for example, we expect that ISP1 can send anything. We expect that R2 should not send routes that come from ISP1, and we expect that if a route is inside the network that originated from ISP1, then it should have a particular community attached. Using these invariants, it's possible to generate local checks in a relatively mechanical way. So for example, there would be one check for R1, checking that it attaches the community. There would be a check for R2, checking that it does the right thing for filtering out routes. And then there would be checks for other routers to make sure that they don't do anything weird. And the results from our work guarantee that if all these checks pass, then the desired end-to-end property holds. And our approach works not just for this property, but it also works for other safety properties, and it works for aliveness properties, which I'm not really going to elaborate on in this presentation. So we tested our tool against Minesweeper, a comparable tool that models the whole network at once using synthetic examples of various sizes. Minesweeper models the network using SMT constraints, and we found that for large examples, for large inputs, it doesn't terminate, and we found that for the inputs it does handle, the time is dominated by the SMT constraint solving time. On the other hand, we found that in our tool, the runtime scales roughly linearly in the number of edges, and only a small fraction of the time is actually spent on solving the constraints. We also perform this type of local checking on configurations from a cloud provider wide area network with hundreds of routers. We use it on a few different scenarios. First, we check the number of properties on the edge routers that peer with the rest of the internet. We also check a more complicated scenario where different IP addresses were used in different regions and communities were used to ensure that this was done correctly. And in both scenarios, we found errors in the BGP configuration. I said earlier that most works model the network as a whole. However, there are a few that do try to apply this modular checking idea. One example is RCDC, which is different from our work in that it tries to verify reachability in the data plane. A much more similar and much more recent work is Timepiece, which does verify the control plane, but it has a very different model of how routing protocols work and a very different way of expressing and specifying the properties and local intents involving a form of temporal logic. So in conclusion, we're proposing that modularity is the key to making control plane verification practical by allowing it to scale linearly and providing actionable feedback on errors. And it does this by leveraging the structure that already exists in network configurations. And in our work, we show how to modularly verify BGP properties. We've formalized and proven this approach, and we've shown that it can scale to checking properties in the WAN of a major cloud provider. Thanks, that is all I have.
Thanks. Great talk. I'm Rulan Yang from Xiamen University. I have a question. So I was wondering how you make sure that your local checks, these conditions you generated, are sound and complete. I mean.
Okay, there's sound in that we have a model of how we in our.
I mean, if I want to check if a reachability, like can S reach D, I mean, there are lots of paths that S can reach D, and you should check all the paths or like all the export-import policies along all these paths, or just to check one path like that?
Okay, so I guess the first part was soundness and completeness. So soundness, we have in our paper, we formalize a model of how we expect BGP to work, and we're showing that our approach should always be sound, given the assumptions of how BGP works in our paper. It is not complete in the sense that it is possible to come up with corner cases where, you might have properties that might be true, but you might not be able to find constraints that will completely prove them, but those tend to be somewhat more complicated, and I'm not entirely sure, and well, maybe you don't want very complicated policies in real networks, but maybe those are used. And then you had another question about different paths. So reachability, so this sort of reachability thing depends on liveness properties, which I did not talk about in the presentation here, but I do mention that is in our paper. And for that, we do consider mostly one path, but it should work in cases where there are multiple paths.
Maybe, if you want to, okay, thanks. Maybe we can discuss offline.
If we have time, we can ask more questions at the end. The next talk is by Yunming Xiao. Yunming is a fifth-year PhD candidate at Northwestern, advised by Alexander Kuzmanovich. He has two primary research interests: security and privacy measures for internet services, and also advancing reliability in data center networks. He is on the job market this year looking for faculty positions or postdocs. And he will be presenting to us. Put up the presentation. You can come. It's good. Yeah. Tensor, lightweight, BGP, nonstop routing.
Thank you. Thank you. Hello, everyone. I'm Yunming Xiao from Northwestern University. Today I'm presenting our work, Tensor, and this work is done together with Tencent, Chaos, and Tsinghua University. Okay, so as we all know, BGP is a sole protocol that stitches autonomous systems together, which are the building blocks of the internet. However, BGP might be interrupted due to either upgrades, which are predictable, or failures, which are unpredictable. We surely want to keep the BGP session alive from predictable disruptions, and this is called nonstop forwarding. To realize NSF, easy way to do is that we notify the other side before such event, and so they can prepare for that. And this has been standardized, and it's called graceful restart. However, keeping the BGP session alive from unpredictable disruptions is much harder, and this capability is called nonstop routing. Unfortunately, failing to do nonstop routing will cause a lot of issues. This is because during a BGP failure, all packets on social link will probably be rerouted or even dropped. And this is a CDF of the average throughput between the links between the Tencent data center and peering ASs. And we can see that if we take the median, that's 64 megabits per second. And that means a 1 minute, one link downtime will impact 500 megabytes of traffic. And if we take the average, the number will go up to 200 gigabytes per link per minute. So naturally, we want to achieve NSR. But there are several challenges lying ahead. First is the virtualization support. So virtualizing the cloud gateway is a current trend for major cloud providers. However, well, I didn't mention here, but there are several previous NSR solutions, but they all rely on some sort of kernel modification, and this obstacles virtualization. And second, we want good performance, and throughput is mostly concerned. Another issue is the previous solutions exist a split brain problem. And by that, it means that both the primary and backup router mistakenly consider the other is down. So both of them are trying to send packets to the other side, and eventually the connection might be disrupted. From the perspective of a distributed system, this is because there isn't enough entity in the system. So for example, for a single point failure, we actually need 3 entities in the system, but while we have primary and backup, that's only 2. Last, we want to improve the system reliability. So existing solutions, they involve modification of kernel, like introducing some wrappers to the TCP or IP stack, modification of BGP, introduce of device management, backend module, and more. But usually, more components involved, the less reliable the system is, and we want to improve that. Okay. So to do that, we present Tensor. At a high level, we have two design pieces. One is we have a kernel modification-free synchronous packet replication, and this provides high system reliability and virtualization support. And second is a lightweight virtualized architecture, which provides performance and solves the split brain problem. Okay, so let's go into details. First, we should know why kernel is always involved in the previous NSR solutions. What if we just replicate the BGP messages at application layer? Let's have an example. So the pairing gateway router is sending 3 packets to our router. And what happens is that these packets will arrive at the kernel and then be delivered to the user space program, where we do the synchronization. However, at the meantime, the kernel will create acknowledgement packets for these received packets and send them back to the peering router. And this might happen. Our router has acknowledged all the packets. However, the synchronization has only just started. So if our router goes down at this time, the backup router will take over the session. However, the peering router has received all the acknowledgements, so it has cleared its sending buffer, and it's sending something new. So the packets 2 and 3 is missing forever, and some inconsistency occurred. So how do we do that? Our solution is very simple. What we do is leverage NetFilter hook to intercept the outgoing acknowledgement packets. And since NetFilter is a Linux subsystem, this does not modify the kernel. And we delay these TCP acknowledgements until the packets, corresponding packets, are properly replicated to the database. Okay. And by doing that, we avoid kernel modification and provide virtualization support. And also, we minimize the involved components. Right now, we only need to modify the BGP program without doing anything else. And this substantially improves the system reliability. Of course, this comes with some downside, is that the delayed acknowledgement impacts performance. But this applies to other NSR solutions as well. So let's take a closer look. The x-axis of this plot is acknowledgement delay, and y-axis is the maximum throughput. We can see that overall, the maximum throughput decreases as the acknowledgement delay increases. But there appears to be a threshold where before that, the throughput will not be impacted. So what we want to do is minimize the performance degradation by limiting the acknowledgement delay. By doing that, we're actually limiting the replication size at a time. So how do we do that? So first, we will virtualize the cloud gateway router. And more importantly, we split the BGP tables that were previously handled by one router to multiple containers. So right now, each container only handles a small fraction of the BGP table. So this minimizes performance degradation of delayed acknowledgement. And also, additional benefits is that it will minimize the impact of a failure. One thing I'd like to mention is that we have an agent server to keep the BFD alive. This is actually not very necessary, but we do it because we want to have a cold start or warm start of backup containers. So BFD is a protocol that used to detect link failures. It is usually accompanied with BGP. And for more details, please refer to our paper. Okay, so we further implement various intercomponent communications that helps us to solve the split brain problem, because right now we have much more entities in the system. We have controller, we have primary container, we have agent server, optionally we have backup container, and we also have many more containers. And yeah, this is more than enough for a single point failure that we'll try to tackle. Next, I'll show some results. So the x-axis is the number of routing updates, and y-axis is the time to process them. And Tensor, our system, is a blue line. The other is other BGP implementations. So we can see at the very beginning, when the number of routing updates are not so much, the with Tensor does not have any performance degradation. And with normal workload, it only adds up to 100 milliseconds to process over 10,000 routing updates. So we can see that Tensor adds only acceptable overhead to process the updates. And when sending out, we actually doesn't have any performance degradation. And last, we show some operational benefits. So for failure recovery, the first line is other BGP implementations. We can see that they actually take tens of seconds or even minutes to recover from a failure. And such recovery is offline, meaning that the other side, the peering router, will acknowledge that this failure and all the packets will be impacted. Instead, Tensor only requires a few seconds to recover, and it's online, meaning that this failure is transparent to the peering router. And compared to the NSR-enabled router, we actually achieve the same level of failure recovery. Both are within seconds. But if we look at the costs, we can see that Tensor requires much less time, much less labor, much less deployment cost, and much less maintenance cost. Yeah. So to conclude, we presented Tensor, a virtualized BGP system that supports NSR capability. And there are two pieces designed. One is kernel modification-free packet replication and lightweight virtualized architecture. And Tensor bears minimal to acceptable performance overhead compared to other BGP implementations while providing the NSR capability. And Tensor will, compared to the NSR-enabled router, Tensor significantly reduces the development, deployment, and maintenance costs. Yeah, that's all my talk. I'll take any questions from you. Thank you.
Thanks. I had two quick questions. The first one is if I want like a BGP session not to die when the link fails, I can also establish, Laurent from ETH. So if I establish the session on loopback addresses instead of the physical address, if there is a link cut, right, I can reroute the TCP connection on another connection. So this is often done inside the network, can also be done on the peering link. So I was wondering how you position there. And the second quick question is, I guess sometimes you really want the BGP session to go down, right? So it's not guaranteed that the link will come back up and that you want it to be there, right? There is a reason why we want BGP to converge, and so I was wondering how you position yourself there.
So I think the question are about like link failures, and when there is a link failure, sure, we should let it down. But our work is mostly on the gateway router. So previously, if gateway router goes down, then everything goes down, even the link. Well, the physical link is fine, right? So our work is more about the gateway router. Yeah.
Okay. And the loopback addresses, did you think of that?
Could you repeat the problem?
So you can establish a BGP session on non-physical addresses, but on virtual addresses or loopback addresses. And then it's kind of like you're virtualizing the BGP session so that it's not binded with the physical link. We can take it offline.
Okay,
that's fine.
sure.
Yes,
yeah,
sure.
Thank you.
Thank you. The final talk of this session is by Dan Halperin. Dan is very happy to be here for his first SIGCOMM since Toronto. And he was the head of engineering at IntentionNet and now leads a team on automated reasoning tools, like network verification to make AWS network even faster. He will be presenting to us on an experience paper on lessons from the evolution of Batfish configuration analysis tools.
Dave, I don't know how to use your PowerPoint.
Is that it? That's the one you got right there? Yeah.
How do I get to the right view?
Oh yeah, the Windows.
I can just try it like this. Is it working up there? If I do that? No, it's not. You tell me what works, I'll do it. I'll just go with the. No, can you just go back the other way, and then I'll just talk from the slides.
That's PC only. That's just this.
Yeah. Yeah. Oh, no, I'm sorry. My bad. Can we just go to duplicate? Yeah? All right. Here's the mouse.
All right. I'm excited to tell you what we've been doing for the last 11 years, putting Batfish into production for real networks. So Batfish started in 2012. That is when the first Git commit happened. It was a project from Microsoft, USC, and UCLA, trying to build proactive network verification. The paper was written in 2015. And in 2017, Ari, Ratul, and Todd founded IntentionNet, and also we started an open source project to kind of bring Batfish to the world. We spent the last 6 years turning this into a project that really works in production. So Batfish is in the open source. We have 1,700 users in our Slack channels. Batfish technology is used at 50 companies and organizations. Batfish actually forms the heart of Oracle Cloud's network path analyzer that lets users understand how their cloud resources are connected or not connected deliberately. And it's also become a foundation for research for more than 20 publications, including perhaps some of the ones in this session. In 2022, all the authors of Batfish actually joined Amazon, where we're taking this same technology and trying to make one of the world's biggest and highest SLA networks much better. And if you want a real sign of success in the open source world, we are getting ChatGPT hallucinations in our open source bug reports. So, there's real users out there. So Batfish came to be in this world where network verification was a new idea, right? So the idea is a great one. If you can go to your live network and snapshot all the data plane state, then you can use a new class of mathematical automated reasoning techniques to find bugs in your network. But what Batfish wanted to do was make this proactive, right? What if this link goes down? What if I make this configuration change? How is the network going to respond to this, and will it still be safe? You can't do that with snapshots. You need something else. And so the idea was, hey, if we can somehow get from device configuration to understanding and proving things about the network, then we can do this ahead of time. We can say, what if I change this? What's the network going to look like, and will I still be safe? And we can also model responses to things like failures, weird BGP advertisements from neighbors, and things like that. And so we built a 4-stage pipeline to do this. The first one is we parse these device configuration files with Antler, and that builds up a model of a device where we know what interfaces it has, what routing sessions it has, things like that. Then we used Datalog to actually do the routing simulation to compute the ribs and fibs of the network. Logic Blocks was nice because it had stratified evaluation, where you could actually handle the non-monotonicity of real networks as you learn new facts, the best paths change. And it also kept provenance for you, so you could kind of understand why these things were there in the first place later. We then used a Datalog extension of the network to actually generate an SMT program that you could then solve with Z3 that would say, hey, given a policy, either it holds and there's no violations, or here's a counterexample, some violating flow, that we then feed back into logic blocks to say, hey, give me the concrete path through the network, and tell me why that path works. Tell me why this route entry is there, because it came from this protocol in OSPF via that static route, for example. And then we sort of gave the explanation back to the user. So here we are, somewhere between 11 and 8 years later. What's changed? Well, it turns out that this pipeline actually is really robust. It's pretty much still how it works today. But of course, every single one of these steps is completely different. And that enabled us, finally, to make this 1,500 times faster than it was, and at least 400 times larger networks than we looked at in the original 2015 paper. We also added one more new stage, which is an offline analysis that we do closed-loop confirmation, making sure that Batfish results can be trusted. So obviously, this is a pretty short 10-minute talk, so I can't go into all the details, but here are kind of 5 of the key lessons we learned in building Batfish. So the first one is that Datalog didn't really grow with us to production. And there were 3 key reasons for this. The first one is expressiveness. If you go look at real configurations, they do things like have regular expressions over BGP community lists rendered in an utterly ridiculous vendor-specific language, where we convert numbers to number colon number, except if it happens to be one of a couple well-known strings. And this kind of stuff is just really hard to express in Datalog, and even if it is, it's really hard to maintain. The second one was performance. It turns out that by design, high-level declarative languages like Datalog, they're all set up to hide execution details from you. You shouldn't have to care about the execution strategy of this thing. Of course, in networking, to get any kind of performance or scale, you really need to control this. If you want OSPF to converge before BGP, so it's not changing the best paths and having them propagate everywhere and then having to redo all that work and keep all that state around. The last thing was we actually had to help networks converge in Batfish. So of course, in a real network, there's all these physical constraints. Time happens, and things that kind of shouldn't converge do, because things happen before each other. And when you have this kind of nice lockstep evaluation strategy, something like Datalog, you can easily get loops because everyone switches to each other's best paths, continuously, exactly in lockstep. When in the real world, the time on the wire would break these ties. And so the solution to this problem was the same. We basically just threw Datalog out and wrote some Java code. That let us both add tons and tons of new features. It also made it 1,500 times faster just by kind of imperatively specifying how these routers work and applying lots of tricks as needed to help the process scale. So I really don't have enough time to do this justice. You have to look in the paper. But the TLDR is that the SNT and Datalog verification story we had didn't scale. The data plane got 1,500 times faster to compute, and now verification was really slowing us down. And I guess you heard a hint from one of the earlier talks that that was going to be a problem. So the solution we had was basically throw Z3 out and use BDDs. BDDs are this incredible tool, and the core BDD engine we have is really simple. It's like 4,800 lines of code, and it's really performant. We can now do data plane verification for networks with thousands of nodes in tens of milliseconds. So it really scales great. Now, one of the things we heard when we were getting started was, you're trying to model a network from configs. That's never going to work. Cisco's going to produce some patch release. Your config is going to have completely different behavior. Your model's going to be totally wrong. Honestly, we never really found that to be a problem at all. If you think about it, commercial vendors would be out of a job if the config you backed up yesterday didn't at all work today when you upgraded your router. Instead, what happened is that all kinds of undocumented behavior that you find when users generate configurations, that's the real challenge. Do you know what happens when a route map that is used in a BGP import policy isn't actually configured on the box? The answer is, they certainly don't tell you in the docs. It depends on every vendor. It depends on what the route map is used in. And the only way to figure it out is to go test. So of course, the solution for this was we built a whole systematic strategy for doing differential testing, where you make sure that your system lines up with what the real OS does in an emulator. And if you're familiar with Hoyan, this is one of the places we have to diverge, right? Because we're looking for, at general third-party networks, we can't do kind of closed-loop validation with the network, but we also, this is how you get around that. So when we first exposed Batfish to users, this reachability technology, we said, here's a Swiss Army knife. Input some path constraints, input some header constraints, maybe add a waypoint constraint. And then, if there's an example that fits that space, we'll find one for you. That's your counterexample. But users, NDEs, are used to traceroute. I log into a box, and I do a ping, and I see a concrete result. So if you give them a tool like, hey, I can answer questions like host A should be able to reach host B, well, it's hard to map this kind of existential quantifiers, universal quantifiers, back down to, well, I log into a box, and I try one path, and it works. And so it turns out that, for example, a statement like this, it might be an all-to-all query. It might be a one-to-many query. It might be actually kind of a weird, strangely reverse one-to-many query. The way we got around this was we built custom assertions, where we basically let users have English sentences kind of like this, and then we'd give them presentations that actually lined up with what they asked. Now, we built Batfish for data plane verification, and we thought that was kind of the key use case. One thing that surprised us was that, in fact, the earlier stages ended up being really useful to lots of users. So in order to do this right, we model the config, and we also model it in the vendor-specific semantics. So we know how Juniper inheritance and weird configuration modeling constructs work. And then we also convert this into the VI model, vendor-independent model. And so that first step lets companies throw out entire classes of tools they've built that just look for regexes in config to make sure that SSH configuration is there, and found a ton of bugs. That second stage has been kind of a one-stop shop for network inventory. Without logging into boxes, you can make sure that everyone has different IP addresses, or BGP sessions will come up. So obviously, there's a lot more to talk about, but I'm at 9:19 with some delays. So go read the paper. There's design, if you can see about how we designed the system, you can read a lot of user stories, and you can have the data to back it up. If I have one piece of advice for this community, coming back after 12 years, it's to try to tackle the unsolved problems. So honestly, like BGP-only networks with no aggregation, with no kind of weird trickery to scale, with no designs about what happens under failures, that's solved. Let's go take on big control plane complexity issues, and let's also take on how users can actually use these results. Finally, we've been at Amazon for about a year. We're trying to put this stuff into production for one of the most fun networks to work on in the world. And so if you're interested, we're starting to hire again. So that's it. Thanks.
Hey, great talk. I really like it. Andor from Tempo. So I'm just curious. So you mentioned limitation of dialogue, right? Expressiveness, performance. So I'm wondering, have you considered Prolog, which is obviously more expressive? It also allows you to control the actual computation.
So if the question was, have we considered Prolog? The answer is, right. I haven't. We found BDDs and just our Java engine to be so great that we didn't really look around, but it might be a really interesting question.
Thank you.
Yeah, thank you. Thank you for sharing. And this is Wei Rong from ByteDance TikTok. Quick question. So you mentioned your solution for the fidelity is test the output of the Batfish against emulator, right? So my question is, how can you make sure the behavior emulator match the real production?
So the question is, how do we make sure that the virtual OSs supplied by vendors match real devices? It's tough. It's not perfect. I think for things like what happens if you don't put a route map in, it works pretty well. As you can imagine, in bigger networks, or especially when we had tighter relationships with users, we also did closed-loop validation with the real network, using kind of offline data dumps and a lot of trickery to make it happen. At the end of the day, of course, you need all of these things, but you get really far just by loading up something in GNS3 or your platform of choice and just setting up a 2-node session and making a bug and seeing what happens.
All right, thank you.
Thank you. Shane from Southern Eyes. So the simulation of BGP is really a tough question. So, but like for a larger scale network, such as AWS and also Meta, that the geographical factor can sometimes play great impact. So can this two also incorporate the geographical information into that? Thank you.
Can you say more about how geography manifests?
Yeah,
it could be latency or isolation.
Yeah, latency. Like large network usually depends on different XPs to deploy their network, and they can be have extensive footprint. So it can bring some difference here.
Maybe we should talk offline about what kinds of properties you're envisioning, but yeah.
Let's thank the speaker. So, actually, we have a few more minutes left for the mini panel, which the TPC chairs have asked for. So I'll ask the other presenters to come back up. And first, I'll ask the presenters if they have questions to each other, especially that there was both an experience paper and non-experience research track papers. If you guys have questions for each other, otherwise I will maybe ask you guys specific questions to ask each other. We can also take questions from the audience. I know Ethan had a question for the first talk. Okay. Dan, I have a question for you. You published an experience paper, and you were also giving feedback to the community. I'm curious, based on your experience from the problems that you've seen in the research track, what are some things that might have been potentially blind spots, or that if you were to work on these problems at a research track or one of them, you would have wanted to tackle very early as you start moving that project to production?
So, if you want. Oh yeah, sorry. Does this work? Does this work? Yeah, okay. So I think one thing I want to compliment this session on is I think we're starting to get at some of the really heart of the problems. I think, as you may or may not know, Batfish is focused on safety of changes. Will the network work afterwards? The number of events in a hyperscaler where the configuration is correct when it starts and correct when it ends, but there are articles written about it, is not zero. Because what happens as you withdraw routes and your backups aren't there is really tough. I forget whose point it was, like BGP add path is a great thing, and in fact, making sure you have backup routes in case you lose your primary route is like a knob. Like that kind of thing, we should just assume that's there from the ground up because that's one of the key knobs that we use. I was really excited about the Lightyear work. I think, especially in a WAN, like you have these policies and actually a WAN is one of the places where you do want information to kind of go everywhere. But I'm also really curious, like, what happens if there's aggregation, for example? Let's say we aggregate a bunch of these routes up together, and Juniper does things like merge all the communities onto a route, and then those routes get resent back to ISP2. Like, how can we adapt these systems, or how do they already handle those kinds of problems?
The issue with the aggregation is I don't think I personally had access to very many examples of configurations that had complex aggregation things, so there was nothing that I could really think about for that one. I don't know if I have any other comment on that.
I had one more random idea, which is that one of the things we often hide when we're tackling these problems is that the network got into this bad state from somewhere else. So for example, I was talking with someone earlier about repair. Right? And so one of the things is, if the network is broken right now, it probably worked 5 minutes ago. And so, maybe you can leverage information you had 5 minutes ago to inform your repair. Even if it's, it might be a config change or it might not. And I think similarly, the reason I brought that up now is, I'm also curious how hard it is to evolve these policies. So, your TE team at whatever cloud WAN you worked with, Microsoft, they want to change which BGP peer they're peering with in Mumbai. Like, how hard is it for especially for the operators themselves, to go change the Lightyear policies to fit the new policy and then also kind of iterate? Those are the kinds of things I would encourage folks to think about.
Do you have no, it's like, okay, feedback, good. I actually had a question. Is there a question from the, we can take questions from the crowd. There is one. Here, yeah, Ethan, thank you. Go ahead.
Is this on? Yeah, great session. Thanks, everybody. I had a question at the end of the first talk, and now I've forgotten some of the details, so I might not get this exactly right. But if I remember right, you started with a comparison point of something like running 2 tables everywhere and then switching over once everything's converged, and the problem with that is the overhead. I liked your solution, but you're adding additional things like dynamically configuring new BGP sessions and running this optimizer. So in what cases is that overhead worth it compared to the overhead of just the simpler approach? Like, does that overhead ever become too much compared to the other one?
So it's a very good question. I don't really know how to answer that. It really depends. Like so sometimes the overhead that you need to add for running both the initial and the final configuration can be very big. Like if there is a lot of state, like if you have to carry the entire BGP table twice, that might already be too much for some routers. Well, on the other hand, if you just want to change something very small and you even know that it's fine, then running this entire thing of Chameleon might also be too much. So I guess it depends a bit on the scenario, on the case.
Can you give some intuition for how many of these temporary sessions you add in realistic networks under different scenarios? And also, do you think that if I had a network, I would be able to reason about, which of these approaches is better for my network or for a certain scenario or something?
That's a good question. So, like for instance, when you have a full mesh, then you don't need any temporary session, as well as if you have add path, then you probably don't need them. Where it really gets bad is if you have exactly one route reflector in the network, then you need temporary session for almost everyone. So if you have multiple of them in our experiments, we see that we need like not that many. It depends, of course, on how the topology looks like, because sometimes we need to do like so that we can avoid transient loops. So in general, what we have seen is like in the order of 10 temporary sessions for like a reconfiguration maybe of 100 routers.
Great. Well, we're at time, 2:30. We have a 15-minute break, after which the next session is going to start in 15 minutes, and it's going to be well tested. Let's thank the speakers one last time.